All right, welcome everyone to this Masterclass Explainer. I'm going to be your professor today for the 42 Piscine C05 module. Today, we're going to break down every single exercise in this module, completely demystify the logic, and give you the exact tools you need to build some truly bulletproof code. We're going to go from basic mathematical loops all the way to complex algorithmic problem solving. So grab your notes because we have a lot of fascinating ground to cover.
So here's our syllabus for today. We're looking at passing the Moulinette, the foundations of iteration versus recursion, applied sequences with Fibonacci and roots, algorithmic efficiency with prime numbers, and finally, the big one, the 10 queens backtracking puzzle. Let's get right into it.
Section 1. The syllabus and, more importantly, passing the Moulinette.
Listen, our main goal here is pretty simple. Write code that sails through the Moulinette's automated checks without a hitch. And honestly, the biggest sigh of relief for these early exercises, you absolutely do not need to worry about handling integer overflow. Yeah, if your calculated factorial or exponent gets too big for a standard C integer, the return value is just officially considered undefined. So, take a breath, focus strictly on the core logic, and just don't stress over complex overflow protection right now.
Moving right along to Section 2, Foundations, Iteration versus Recursion. Okay, so we're looking at exercises 00 through 03, where you literally have to solve factorials and powers twice, once with iteration and once with recursion. Which brings up a really great question. How do iteration and recursion fundamentally differ when you're solving the exact same mathematical problem? I mean, both are going to get you to the exact same destination, but the vehicle you drive to get there, totally different. So let's break down those two vehicles. On side A, we've got the iterative approach. You'll use this for exercises 00 and 02. This is your trusty while or for loop. You know the drill. Set a variable, loop through, multiply, and just accumulate that product step by step until your condition is met. But then, on side B, we have recursion, which is for exercises 01 and 03. And this is where the function actually calls itself. It basically takes a slightly smaller piece of the puzzle every single time until it hits rock bottom, and then it passes all the answers back up the chain. Now, before you even think about writing a loop or a recursive call, we've got to talk about edge cases. For the factorials in exercises 00 and 01, any negative argument passed in has to return 0, period. And for the powers in exercises 02 and 03, if the exponent is strictly lower than 0, again, return 0. Here is a massive tip from me to you. Put these negative checks at the very top of your functions. Seriously, if a bad input comes your way, you want to catch it immediately and return 0 before your code even dreams of entering a loop or piling up a recursive stack.
And speaking of that recursive stack, when you write those recursive versions, you absolutely must have a base case. This is that crucial make or break condition that literally stops a recursive function from calling itself into infinity and totally crashing your program. Think of recursion like walking down a staircase in the dark. The base case, that's the solid floor at the bottom so you don't fall forever.
And for exercises 00 through 03, that solid floor is usually the number 1. By mathematical definition, and by the strict rules of this module, the factorial of 0, 0 explanation point, has to return 1. And similarly, the module explicitly dictates that 0 to the power of 0 must also return 1. So if you lock these definitions right into your base cases, your recursive functions are going to resolve beautifully.
All right, let's look at Section 3, Applied Sequences, covering Fibonacci and roots. So, for exercises 04 and 5, we're shifting gears from just basic arithmetic over to actually generating sequences. Exercise 04 wants you to find the nth element of the Fibonacci sequence using pure recursion. Remember, every number is just the sum of the two before it. But as we just learned, a recursive function needs starting rules, right? Your constraints here are super specific. If the requested index is strictly lower than 0, you return -1. If it's 0, return 0. If it's 1, return 1. Just code those base cases right at the top, and then your recursive call simply becomes returning the function of index -1 plus the function of index -2. Super clean.
Then we hit exercise 05, ft_square root, where we have to find an integer square root. And the catch? No external math libraries allowed. We're building this from scratch. So here's a foolproof 3-step algorithm for you. Step 1. Start a simple integer loop beginning at 1. Step 2. Multiply that index by itself. If the index times the index exactly equals your target number, boom, you found the square root. You just return the index. But step 3, If index times index grows larger than your target number, you've gone too far. You overshot it. Break that loop immediately and return 0.
And listen, the Moulinette is absolutely going to try and trap you on this square root exercise, so pay attention here. First off, negative numbers do not have real square roots in this context, so instantly return 0. Second, and this is a big one, if the square root is a fractional or irrational number, like say the square root of 5, your function must fail cleanly and return 0. It is strictly looking for whole integers. And finally, stopping that loop early when your multiplication exceeds the target, that's not just a good coding habit. It's going to save you from infinite loops and massive performance timeouts.
Which perfectly tees up Section 4, algorithmic efficiency and conquering prime numbers.
Look, up until now, just getting the code to work was pretty much enough. But for exercises 06 and 07, which deal with prime numbers, your code actually has to be mathematically efficient too. For exercise 06, ft is prime, you've got to memorize this rule. The numbers 0 and 1 are explicitly not prime numbers. So if your function gets a 0, a 1, or honestly any negative number, it needs to immediately return 0.
Now here is the ultimate mathematical shortcut to save your processing power. To check if a number is prime, you do not need to check if it's divisible by every single number all the way up to itself. You literally only need to check up to its square root. So, Step 1. Filter out those numbers less than or equal to 1. Step 2. Create a loop starting at 2 and keep it running as long as your iterator times itself is less than or equal to your target. If the target modulo the iterator equals 0 at any point, its composite return 0. But if that loop finishes clean without any hits, return 1. You've got a prime.
And honestly, exercise 07, ft find next prime. That one is practically a freebie if you just nailed exercise 06. All you're doing is writing a function that takes a number, and if it's prime, it returns it. If it's not prime, it just increments the number and checks again. Just take that brilliant, optimized prime checking logic you just wrote, wrap the whole thing inside a while loop, and increment your target variable until you hit a prime. Easy as that.
All right, we've made it. Section 5, the final exam, the 10 queens backtracking puzzle.
Okay, take a deep breath for this one. This is usually the exercise that separates the coders from the software engineers. The prompt is asking you to find every single possible way to place 10 chess queens on a 10 by 10 board so that none of them can attack each other. And to do this, we use a backtracking algorithm. Now, I know backtracking sounds super intimidating, but I promise it's really just a simple trial and error process that has a memory. You place a queen, you move to the next column. If you get stuck because every single square in that new column is under attack, you backtrack, meaning you just go back to the previous column, pick up the queen you left there, and try putting her in the next available spot.
So let's whiteboard this out into a really clear 4-step plan. Step 1, your recursive function is going to iterate through the columns from 0 to 9. Step 2, inside that column, you try a row. You check if that specific row and its diagonals are completely safe from any previously placed queens. Step 3, if it is safe, you temporarily place the queen there and then recursively call your function to move on to the next column. And step 4, this is your base case. If your recursive function is ever called for column 10, that means you successfully placed queens in column 0 through 9. You actually found a valid board. So you just print it out, increment your total solutions counter, and return. Now, I want to give you a massive tip regarding your implementation constraints here. Please, do not try to build a two-dimensional 10 by 10 matrix for your chessboard. It is wildly inefficient. Instead, just use a simple one-dimensional integer array of size 10. The index of the array is going to represent the column, and the actual integer stored inside that index represents the row where the queen lives. So for example, if array index 0 equals 5, that just means in column 0, the queen is sitting on row 5. This makes printing your solution incredibly easy because the required output format actually matches this array reading exactly from left to right. Oh, and keep in mind, the only external function you're allowed to use here is right. Okay, zooming back in on step 2, the safety check. To do this, you have to loop through all your previously placed columns. If the row of a previous queen matches your current row, well, that's a threat. But how do you check the diagonals mathematically? It's a neat trick. You compare absolute differences. If the absolute difference between the two rows is exactly equal to the absolute difference between the two columns, those queens are sitting on the exact same diagonal and they're threatening each other. Code that logic in, and your queens will safely navigate the board every single time.
By mastering these specific exercises, going from simple while loops all the way to a full backtracking algorithm, you are building the exact foundational muscles you need for advanced computer science. It's a huge milestone. So, I want to leave you with this question to ponder. Once you master backtracking on a chessboard, what other complex software engineering problems can you recursively dismantle? Pathfinding algorithms? Sudoku solvers? The logic you learned here today literally unlocks all of it. Best of luck on the Moulinette class, write clean code, double-check those base cases, and I will see you in the next Masterclass Explainer.